Hello everyone. Today is the second lecture of numerical solution of differential equations. In the first lecture, we had a long discussion on ordinary differential equation, solving numerically, error analysis, and different types of method, implicit, explicit method. And also lastly, we talked about Taylor series expansion. Now today we'll have, let's start with a single step multi-step method. Already we discussed about that. The methods for the initial value problem. The problem is given by equation 1, first order differential equation dy dx equal to function of xy, and initial values are given y at x naught equal to y naught. So single step method is if the value of y plus y bar I plus 1 depends on the knowledge of the preceding value yi bar, and if the value of yi plus 1 bar depends on more than one of the preceding values, yi bar, yi minus 1 bar, etc., then that is called multi-step method. So single step methods mean yi plus 1 bar depends on the knowledge of the preceding value, only one preceding value, yi bar. But in multi-step method, you see yi plus 1 bar depends on more than one preceding values. So that is the difference between single step and multi-step method. Now, so a general single step method, as we discussed, Taylor's expansion, Taylor's theorem. If you apply on x plus h, then it will be given by yx plus h, yx, h, y prime x, h square by factorial to y double prime x, etc. And hp by factorial p, ypx, that is the pth order derivative. And lastly, you have the error term, and 0 less than theta less than 1, that you all of us know about the Taylor's theorem. Since yp plus 1x is continuous in closed interval ab, it is bounded therein, and it follows that the last term order of h plus h to the power p plus 1, look at the last term, this is the last term, so that we may write, if you write the last term as order of hp plus 1, we may write this is written as yx plus h, this is written as x plus h equal to yx, and the rest of the term, that is this part, you can write h, you can take h common and you can write phi t. Phi t is this whole expression, phi t of function of x, y, h. And lastly, you have order of h plus h to the power p plus 1. This is equation 2. Now, already explains what is your phi t. Now y prime, y double prime, yp being expressed as functions of x and y in terms of f and its partial derivatives. Now equation 3 gives a general single step method for of the pth order. So what is your equation 3? Equation 3 is nothing but a general single step method. This is your single step method of order p. The method is present form is however largely theoretical for the successively calculations of partial derivatives, because you have to calculate partial derivatives fx, fxy, f double dash, f xx, so on. So you have to calculate this is you have to substitute the previous one, and successive calculation of partial derivatives become increasingly complicated, so that even for moderate value of p, the computation of phi t, xi, yi bar, h at every c step might call for prohibited amount of labor. So it's very laborious method. So for successive iterations, you have to calculate a lot of partial derivatives for getting a moderate value of p. Okay, so this step is a single step method, and there are a lot of disadvantage of this method. Next is, if we talk about PICARD iteration. Okay, PICARD'S method for solving differential equation. So this is the PICARD, famous mathematician. PICARD'S method is an alternative method for finding a solution to differential equations. It uses successive approximations in order to estimate what a solution would look like. The approximations resemble Taylor series expansion. It's just like a Taylor series expansion, as with Taylor series, when taken to infinity, they ceases to be approximations and become the function they are approximating. Now, so this is the initial value problem, dy dx equal to fxy and yx naught equal to y naught. Now let us integrate between x naught and x1 both sides. Then you have y at x1 minus y x naught equal to x naught to x ft yt dt, and yx equal to, if you write yx equal to yx naught x naught to integration x naught to x ft yt dt. Now you continue with the process, you will get a iteration steps. So this is written as phi 1x, the first iteration, and you continue, you will get phi 2, phi 3, phi n, etc. This is the nth iteration formula. Phi nx equal to yx naught integration x naught to x ft, a function of t phi n t dt. Okay, so this is the iteration by PICARD'S method. Now let's have an example on that. Dy dx equal to y, y0 equal to 1. If you apply your PICARD'S first iteration phi 1x, so 1, because y0 is 1, initial value is 1, so initial approximation 1, 0 to x phi naught t dt, so you calculate 1 plus x. Next iteration phi 2 is 1 plus x square by 2. It's like Taylor series, phi 3x, you will get this one, and the nth iteration is given by this one. So PICARD'S method is integral to the Picard-Lendolif theorem of existence and uniqueness of solution to differential equations. It uses the fact that these successive integral approximations converge, which allows you to claim that for a certain region that the solution is unique. So this is about your PICARD'S method. So Picard method is integral to the Picard-Lendolif theorem of existence and unique solution to differential equation. Okay, and let's come to next, the most important one, that is Euler's method. We'll talk about Euler's method. This is also single step method. So Euler's method for p equal to 1. For p equal to 1, equation 3 reduces to this. So what was your equation 3? Equation 3 was actually p equal to, for phi t, the expression for phi t. Let's have equation 3. Let's find out equation 3. Yeah, this is your equation 3. Look at that. This is for pth order pth order, phi t. Now for p equal to 1, you are remain with phi t x y h y prime x, first order derivative with respect to. Okay. So yeah, this is your equation 4 now. Y dash x equal to f of function of xy, and the recursion is given by y naught bar equal to y naught and yi plus 1 bar equal to yi bar h f of xi yi bar. This is the recursion formula, and this is the single step explicit method of order 1. This single step explicit method of order 1 is known as Euler method or the tangent line method. Okay, this is a single step explicit method, and this is the formula for Euler's method. Now Euler's method is the simplest and the most crude of all single step methods. Simple method, but it is crude and has a very little accuracy. Accuracy is very less. As such, the method is used only when you are have a rough idea about the solution is out for. So if you have a rough idea of the solution, then you can apply Euler's method. Otherwise, don't. It's a single step explicit method only. So there is no use of that. Now let us have a geometrical interpretation. So this is the geometrical interpretation. geometrical interpretation. So look at that. This is your fi xi is the slope of the exact solution curve y equal to a yx at the point xi yi. So this is the point, this is the point P, and this is y equal to yx curve. This curve is actually y equal to yx, and this is the point xi yi. Okay, P is the point xi yi. So fxi is the slope of the exact solution curve at the point xi yi on it. Let okay, so P is the point xi yi, and let's draw the tangent. PH is the tangent, and PM from PM denote the ordinate at the point xi yi, and Qn denote the ordinate at the point, this point is suppose xi plus 1 comma yi plus 1. Okay, and Qn denote the ordinate at this point Qn. If you draw the perpendicular from Qn is the perpendicular. Okay, let the tangent, this is the tangent, PH is the tangent, okay, at xi yi. PH is the tangent at xi, and intersect the ordinate at h, ordinate Qn at h, and from P you draw the perpendicular PG. PG be the perpendicular from P to Qn. Okay, clear? The notations are clear? Then PG equal to Mn equal to h. This is also h, this is also h. Okay, look at the formula for Euler's. Yi bar plus 1 equal to yi bar plus h into fxi yi bar. So you see, this is your xi, P is the point xi yi, and this is your xi plus 1 yi plus 1, and pH is the tangent at that point. That is the given by equation of the tangent actually. This is the equation of the tangent. Actually this formula, Euler's formula, is the tangent at that point. It gives you the tangent at that point. And h is the step length. So, and Ag equal to, what is your Ag if you calculate this angle? What is your Ag? Ag is equal to h. What is your Ag? Ag equal to, from this triangle actually, PGH. If you take the triangle PGH, then you can write Ag equal to h f of xi comma yi, xi comma yi. Okay, so h f of xi comma yi. So according to that equation, Euler's equation, we can write, according to equation 4, Euler explicit method predicts the ordinate at the abscissa xi plus 1 to be hn equal to pm plus hg. Look at the diagram. So from the Euler's formula, you have hn. According to that formula, hn, this hn equal to ag plus gn, pm, okay, and gn is nothing but your pm. So you can write ag plus pm. Okay, so that is written here, ag plus pm hn, instead of the true value qn, but the true value is qn. Look at the diagram. So this is the error, hq is the error, this is the error part, okay, and qn is the true value. Okay, so this is the error in computation. So look at that, it's a very less effective method, and there is a error will be more if you apply Euler's formula. So that is why you are not forced to use Euler's formula in general. Okay, so that is the geometrical interpretation of Euler's method. Now we have more. I will show you in another way. I will show you Euler's formula. So For a point x2 close to x1, we approximate phi x2 using the in another way, using the line passing through x1 y1 with slope f of x1 y1. Actually, slope is f of x1 y1. So this is the y2. Thus, we create a sequence yn of approximation to phi xn, and that is given by this sequence of iterations. For a uniform step size h equal to xn minus xn minus 1, Euler's formula becomes this. This is the formula as already we have discussed. This is in another form actually I am writing. So Euler's formula approximation, to graph an Euler approximation, we plot the point x0 y0. You are getting x0 y0, x1 y1, x2 y2, xn yn. So successively you are getting these values. So if you plot this point, you will have a polygonal trench. It's like a polygonal trench. If you connect them with a straight line, it will looks like this. This is the connect these points with the line segments. Okay, these are all line segments. Now the first step of Euler method uses the tangent line to phi at the point x1 x0 y0 in order to estimate phi x1 with y1. The point x1 y1 is typically not the graph of phi, because y1 is an approximation to phi of x1. Thus the next iteration of Euler's method does not use a tangent line approximation to phi, but rather to a nearby solution phi 1 that passes through the point x1 y1. Thus Euler's method uses a succession of tangent lines to a sequence of different solutions phi 1, phi 2 of the differential equation. So more clear diagram will be this one. This one will be more clear diagram. So we look at that first point x1 x0 is the initial point x0 y0, and here you can draw the tangent line. So tangent line at the point x1 y1 to the exact solution to the IVP, initial value problem. Now you have a point x1 y1. So x1 y1, this is the true value x1 y x1, but this is the true value x1 y1, and this is the approximate value, the approximation by tangent. So so you have again a tangent. You draw a tangent at x1 y1, and this is the solution curve through x1 y1. This is the solution curve. Okay, it's written, this is the solution curve. Look at that, the curve, and the tangent at x1 y1. Again you can draw the solution curve. So it's away from the exact solution to IVP. You look at that. This is the exact solution. This is the exact solution to initial value problem. But here you see the graph is actually away, and you have a series of tangent lines. You draw the tangent lines, then the curve. So you are getting a new solution curve. The new solution curve is away from the exact solution. So this is the clear picture of Euler's method of approximate the solution to the initial value problem. Okay, and this gives you a geometrical idea also. Now I will move to, and also the local truncation error of Euler's method is order of h square, and this error is actually global error is also order of h square. So next we'll discuss about modified Euler's method. So in modified Euler's method, there is no scope. In Euler's method, actually there is no scope to improve the value of y. The improvement can be done using modified Euler's method because of that disadvantage. Because of that disadvantage that the solution of the by Euler's method is it's away from the exact solution of the initial value problem. So what we do, again we are writing the initial value problem, that is equation 7. Now to obtain the solution x1, integrate over x0 x1. That is, if you integrate both sides, you have which gives x0 to x1 y1 and x0 to fxy dx. Now the integration of RHS can be done using any numerical method. If the trapezoidal rule is used with step size h equal to x1 minus x0, then above integration becomes y at x1 equal to y x0 plus h by 2. So you are applying trapezoidal rule actually. So this is the formula for trapezoidal rule. Using the step size h equal to x1 minus x0, then the above integration becomes, this integration becomes, the right hand side becomes y at x naught x1 equal to y x naught, that is the next value, y x naught plus h by 2. This comes from the trapezoidal rule, okay, or midpoint rule you can say. Note that the right hand side of 9 involves an unknown quantity y at x1. This is the unknown quantity. This value can be determined by Euler's method. How will you calculate the Euler value y at x1? This value can be calculated by Euler's method, okay. Now this should be 0 iteration you can put here. So Euler's method, you can apply Euler's method to get the value. Let us denote this value by y naught x1 and the value obtained from 9 by y1 x1, okay. So this is by, I am denoting this by y naught x1 as I mentioned here, and the value obtained by 9. If you substitute this value by Euler's method, you will get y1 x1. So this is the current value is y1 x1. Again, if you apply the resulting formula of finding y1 is this one. So now the modified thing is this one. This is the modified. Now this is the modified form. So you are using Euler's, the previous formula, as well as the modified formula. This is the modified formula number 10. This is the modified one. So this is the first approximation of y1. We will have next second approximation of y1. So this is the second approximation of y1. So y12, that is y. So y naught h by 2 f x naught y naught x1 y11. So this is how your values are modified by Euler's modified method. And you will get third approximation, fourth approximation, and so on. And you can write the k plus 1th approximate value of y1 as y1 k plus 1 y naught plus h by 2 function of the value, functional values at x naught y naught plus fx1 y1 k equal to 0 1 2 etc. And finally you can write, this is 13, this should be 13. Finally you can write the method by this, the formulae in terms of iteration, I equal to 1 to 0 to etc 0 1 2 etc, k equal to 0 1 2 etc. So this is by Euler's and this is the Euler's modified. So together will give you the Euler's modified method, okay. The iterations are continued until two successive approximations yi plus 1 k and yi plus k plus 1 coincide to the desired accuracy. So if these two values are coincide, if yk plus 1 and k coincide with desired accuracy, that iteration converge rapidly for sufficient small spacing h. If you take very small h, the method will rapidly converge, okay. So this is, we are talking about Euler's modified method. Now let's have the geometrical part, the most interesting part. So look at that once again. This is the curve, this is the curve. We are talking about solution curve, exact solution to the initial value problem. This is the exact solution, look at that, okay. This is your, and this is the initial point x naught y naught, initial value problem. And at x naught y1 you have drawn the tangent. This is the tangent, suppose t naught. T naught is the tangent at P at this point x naught y naught, and this is the point, this is the point x1 y1 star or y naught y1 naught. Let us write in the geometry y1 naught. This is your x1 y1 naught, the unknown. You can calculate this by Euler's method. So this is the point x1 y1 naught, and this is x1 y1 x, okay. Now let P be the point by P be the point by trapezoidal, or you can apply the midpoint formula, okay. You can apply P is your x naught plus h by 2, and at that point, and this is this dotted line, actually this dotted line actually Euler's approximation at x equal to x1. Look at the dotted line is the approximation at a dotted line is the tangent at that point. Sorry, it's a tangent at that point, and this point is actually the approximation at x equal to x1 by Euler's, and this is the tangent line to solution through x1 y1 0. So this is the tangent line. This dotted line is the tangent line at x1 y1 0. Okay, now through p is by, this is p, this is the coordinate of p, and p is by midpoint, or you can apply trapezoidal. So at p you draw the line through p that is parallel, that is having the slope equal to this dotted line, and that is modified Euler approximation at x1 y1. Okay, so look at that, this solution will come closer to the exact solution to the initial value problem. This is your modified approximation, and you see your modified Euler's approximation is much closer to the exact solution compared to the Euler's approximation. That is the difference you can see from this graph. This is very important graph, very important geometrical implications, that your modified Euler's approximation. So once again, how did you get that modified Euler's approximation? First of all, your Euler's approximation at x equal to x1 is given by x1 y1 0. This point x1 y1 0. In the graph it is denoted by y1 star. Okay, but here x1 y1 0. At x1 y1 0 is you draw the tangent, that is the tangent line to the solution through x1 y1 0. Okay, you draw the tangent, and the tangent is denoted by dotted line in the graph. Now p is the point given by, p is the point that x naught plus h by 2, y naught plus h, that is the point by, you can get the point by trapezoidal. Okay, and through p you draw the line parallel to this, having slope equal to this dotted this tangent line at x1 y1 0. So if you draw the tangent, if you draw the line through p, then that line will cut the ordinate at the true value x equal to x1 at x1 y1. This is the modified Euler approximation at x equal to y1, x equal to x1, modified Euler. So this modified Euler approximation is closer to the actual or exact solution compared to the Euler approximation. So that is how I have described about geometrical applications and geometrical interpretation of Euler's modified method, also comparison with Euler's method. Okay, and that will give you the idea about Euler's method and Euler's method or modified method and their geometrical interpretation. That's all for today, all of you. Thank you.